Hello and welcome to Tomversations, a monthly conversation with me, your host, Tom Hollingsworth, on a variety of enterprise IT topics. Today, I'd like to talk about something that's near and dear to my heart, networking. It's something that I've built my career on, and it's something that I've spent a lot of time researching and understanding. But I'm not talking about any devices or products today. I'm talking about protocols. No, I'm not talking about BGP or RIP or any of those. I'm talking about one of the most fundamental protocols that's involved in networking, and that's TCP. Because I don't know if you've heard this or not, but TCP is dead. Long live TCP. So let's have a conversation about that. First of all, we have to understand what TCP is. Now, a lot of folks that are involved in networking refer to it as TCP IP, and that is accurate. TCP is the Transmission Control Protocol, which allows the IP or Internet Protocol packets to be delivered reliably. Funny thing about IP is it's a phone number. It's a way for you to contact a host, but it has no capability to set up a session between those two hosts. That's what TCP is for. TCP allows you to reliably send packets from one location to the other. It makes sure that the two devices which are speaking to each other are primed and ready for a conversation, and it makes sure that the data is delivered on the other side. Now, you've probably heard of the TCP three-way handshake. Essentially what happens is the device signals that it is ready to send a packet or start a TCP conversation. The receiving host says that it also is ready to receive with an acknowledgement, and then the sending station acknowledges that acknowledgement and sends the packet. So in a way, it's a very deliberate setup. I'm ready to send you something. Are you ready to hear it? Yes, I am ready to hear the thing that you are ready to send me. Okay, I hear that you are ready to hear the thing that I'm about to send you. It sounds kind of clunky, doesn't it? Could you imagine if we had conversations like that on a regular basis? Well, it would make for some very interesting videos for sure. TCP has been around for a long time. How long? Well, as of the recording of this video, 48 years. The original TCP specifications were developed in 1974, back when the internet was still the DARPANET, and it was still a gleam in the eye of every person who ever wanted to argue with people and leave crappy comments on videos. TCP was designed to solve a particular issue. We don't know how reliable the networks are between where we are and the receiving station. So we need to build in the kinds of protections to the protocol that prevents any level higher in the stack from having to worry about fixing those things. Think about all of those cell phone commercials that you had to listen to back in the 90s and the early 2000s. You know the guy, can you hear me now? Well, the reason why those existed was because communications on cell phones were pretty crappy, to be honest with you. Call quality was very low. This analogy basically says that rather than trying to fix the problems in the communications layer between the cell phones, I'm just going to send you everything and you can sort it out. Maybe the words appear out of order. Maybe you need to try to figure out whether or not that was a mangled packet or not, but if it was not mangled, why is the data not matching up with everything else in the stream? But you're having to process that in real time as you're trying to listen to the conversation. Can you see how quickly you could overwhelm a system like that? And remember that back in the day, the processors that were running on these things were, Intel 8088s. They were not designed to do a whole lot of heavy lifting further down the stack. TCP takes care of that for us. It takes care of reliable delivery. It takes care of making sure the conversation happens. Now, there's a cost associated with that, and we all know what that is: overhead. It takes longer for a TCP session to be set up because of that three-way handshake. If a datagram or a packet is not delivered reliably, if there's a problem with the delivery, the first thing that TCP is going to do is go, hold on a minute, we need to stop and you need to send that again. I mean, that's what I would want to do, especially if I'm listening to the data and I'm trying to reassemble it, because the other thing is TCP provides sequence numbers. So if a data packet arrives out of order, TCP knows where to reassemble it. That creates latency. Hundreds of milliseconds of latency, depending on how much has to happen. But remember, we're still thinking in the 1970s and the 1980s. Just being able to send packets across the country was a miracle in and of itself. But as we moved on, we realized that some things are very latency sensitive. The video you're watching right now is very latency sensitive. Why? Because if you are listening to the audio and viewing the video, you don't care if the frames are out of order. If one frame jumps ahead out of how many? 24 frames a second, 30 frames a second, 60 frames a second, it's just going to look like a little glitch. Likewise, audio glitches just sound like a little bit of a garbled transmission, kind of like that cell phone call that we had. If I drop an occasional packet in that call, I can generally get the gist of what's going on. Obviously, higher packet losses are less, understandable. What's really bad is if the audio and the video get delivered out of sync, right? So let's say that the video signals are being delivered properly, but maybe the audio is in a separate stream and it has to do a retransmission. So now the videos and audio are starting to drift out of sync a little bit. Do you see how that could be a problem? Well, most people do. That's why we developed something called UDP, which is the User Datagram Protocol. Imagine if you walked into TCP and got rid of all the junk that wasn't necessary for something to be delivered. Well, we're going to throw the checksum out, the TCP checksum, because we don't need that. IP has a checksum. We're going to throw out the reliable transmission thing. We don't care if those packets show up on the other side. We're just going to blast them out like a fire hose. Essentially, all we care about is setting up that connection and sending packets along it. And then we're going to close the session and move on to the next part, right? So UDP works really well for things that we don't care if they arrive out of order because latency is more critical to us than reliable packet delivery, or when we don't care about the response. So for example, if my device asks a DNS server for a response, the DNS server is going to reply, and I don't care if it got it or not. If it didn't, it'll just ask for it again, right? So things like DNS run over UDP. In fact, a lot of protocols run over, or a lot of higher level protocols run over UDP now, because we're less concerned with reliable transmission. And if you're using anything like multicast or broadcast, that absolutely works over UDP. Why? If I'm multicasting things to a number of stations, I really don't care if they're getting it. I just care that I'm sending it. And if I have to wait for acknowledgments for every packet stream that I'm sending out to those devices, you can see how the sender is going to get overwhelmed pretty quickly. The problem is that UDP doesn't provide reliable connectivity. It'll maybe show up, maybe it won't. We all know the famous UDP joke in networking. I'd tell you a UDP joke, but I don't really care if you got it. One of the alternatives to TCP that a lot of people have been talking about for the last decade is something called QUIC. This was developed by Google. It was originally called the Quick UDP Internet Connections. However, nobody calls it that anymore. QUIC is no longer an acronym. It's just the word that we use to describe this protocol. QUIC is built on top of UDP. Google said, we want to provide a little bit of backwards compatibility for things that are running UDP, but we want to provide other things on top of it, but things that are important to us. The three biggest things are that they wanted to have a very fast setup time. They wanted to be able to deliver multiple streams inside of a quick setup, and they wanted to provide for encryption. Number one is pretty obvious, right? Quick setup time, we want to be able to send that packet as quickly as we can. Two, I want to be able to send multiple streams inside of that. TCP can fake this by having the device send multiple elements in the same stream. That's what's enabled in HTTP version 2. The problem is that when one of those elements is misdelivered, out of order, or mangled in transmission, TCP stops the entire stream from transmitting until it receives the response. That's called head-end blocking. And under certain circumstances, you really want that to work. However, if you're viewing a web page, what I really want is for everything on the web page to load as quickly as possible, because milliseconds are money when it comes to web pages. And if something has to render a little bit slower, like one ad or one element, so be it. The third thing is encryption. We live in a world where everything is encrypted. Almost every communication that we have now, especially when it involves HTTP, is actually delivered over secure HTTP. Well, in TCP, which was developed before HTTP, remember that, we have to do two separate handshakes. We have to do the initial TCP setup, and then we have to do an encryption setup. So some of those packets are sent in the clear, and it does take a few hundred milliseconds more to do that setup. Well, Google said, well, if we're using everything over secure HTTP anyway, why can't we embed the TLS, Transport Layer Security handshake, in The quick handshake. I mean, we're going to be over secure anyway. We might as well set it up that way. And so that's what they did. Quick has been in development for about a decade. It's a part of the HTTP 3.0 standard, and almost everyone uses it, especially if you use a web browser like Google Chrome. But that's really about the only place that it's being used right now, is it's being used in web browsers, because companies like Google and platforms like Chromium are heavily relying on it to be able to deliver all of this stuff. Quick is great if you're trying to send things in an HTTP-like environment. Okay, that makes sense. So why would you need anything else? Well, enter Amazon. Amazon has spent the last couple of years working on their own version of TCP that is specific to challenges that they're facing inside of their data centers. They developed something called SRD, which stands for Secure Reliable Datagram. Why do you want that? Remember how I told you that there's a problem with head-end blocking in TCP, that when I send multiple streams, that if one of the streams is mangled, TCP is going to stop it until it receives the replacement packet for the mangled stream, right? Think about Amazon. They have multiple devices talking to multiple other devices all at the same time, and they're trying to use multipath I/O in order to get everything there as quickly as possible, because that network is being constantly utilized by a huge number of devices. So what they want, ultimately, is they want to be able to send all of the packets for a given stream across multiple paths and have them arrive at the other side as quickly as they can get them there. Except remember that TCP doesn't like it when things arrive out of order. In order to use multipath protocols with TCP, you have to do some really creative things to get those to work right. If you're an old school networking person, you may remember the fact that on a link aggregation channel, like an ether channel, a given TCP stream will only use one of those links, even though they'll be load balanced across them under normal circumstances, because TCP really hates it when you send a packet from a stream on another link. So how did Amazon get around this? Because if you read the papers, like the ones that I linked in the show notes, they're going to say, oh, well, we let that happen higher up the stack. And they do. How high up the stack? About 36 centimeters away. Because what they're actually doing is they're using a data processing unit, a DPU, which is effectively a network I/O offload card to take care of all that monkey business that TCP used to take care of. So I can send all of my packets out of an Amazon Nitro card across multiple different paths. Because when they arrive on the other side, rather than TCP trying to put them back together, the Nitro card is going to look at all of the sequence numbers that are created for those packets, reassemble them before sending them up to a higher level. Remember how I told you that if you had to try to figure out the quality of the link while you're trying to listen to the conversation, that your CPU is going to get overwhelmed? Could you imagine if a server CPU that's already sitting at 80+% utilization because of things like virtualization and containers also had to worry about reassembling all of the packets that were flying in because they were arriving out of order and we didn't use TCP to do that for us? And they're coming faster because TCP is not slowing the connection down to prevent it from being overwhelmed? Yeah, you can see now why a protocol like SRD heavily relies, in fact, requires you to have a DPU in the server that you're sending it to. It's also running over a system that looks very much like InfiniBand, which is not Ethernet. However, it is using InfiniBand technology on Ethernet. The reason why Amazon is trying to implement InfiniBand-like technology but not use InfiniBand is because they have a significant investment in Ethernet. They don't necessarily think that Ethernet is bad. They just don't like the TCP aspect of it. So that's what they're trying to do, is get around the fact that TCP is causing blocking. Because for them, they don't necessarily care so much about reliability as they do about latency. And they have a solution that will allow you to offload any latency issues to a DPU to be able to provide all that stuff to a higher level. All right, so we've covered TCP, we covered UDP, TCP's little brother that runs around screaming and who doesn't care who hears. We've covered Quick, which is Google's attempt to make TCP more secure and run it in a web browser. And then we've covered Amazon SRD, which is Amazon's attempt to make InfiniBand run on Ethernet and have low latency because you need a DPU to fix all the problems that we've already solved. So I guess the question is, why are we still using TCP? Why are we still using a relic from the 70s in our internet? The funny thing is, there's a lot of things that don't really play well when it's not seeing TCP. That reliable transmission that we get, a lot of applications depend on the ability for those packets to be delivered reliably. As much as we like to admit that we live in a modern environment where we have all kinds of connectivity, the truth is that there are still a lot of places in the world where connectivity is not the best. And so over a satellite link, over a very low quality DSL link, over a place where packet loss is much higher than we might anticipate, you still want to use a protocol like TCP. And if you're using anything other than a web browser, you're going to be using a protocol like TCP. One of the other reasons why we still utilize TCP so much is because we've had it for so long that we've just learned to work around the restrictions that TCP gives us. A lot of networking hardware that we have implemented in transit networks is optimized to accelerate TCP. There are ways that we can find around it. Just go back to any QoS that you've ever been studying. One of the very first things that they teach you in QoS is that TCP creates spikes in your network because of the way that it uses backoff timers. And so we've created algorithms inside of devices that essentially fake out TCP to reduce those spikes and create a smaller sawtooth pattern through things like weighted random early detection. That's an entire video in and of itself. But we've learned to work with those limitations. We didn't rewrite the internet to fix TCP. We just figured out how best to work with what TCP gave us. Much like protocols like BGP, the modern internet relies on TCP. We may not like it. We may think it's an old fogey, but it's what we've got. And the challenges that it was built to solve were the challenges that existed before most of us were born. The internet of the 1970s, which isn't even really the internet, looks radically different than the internet of 2020 or 2022 or 2026. If you want to go do research on a number of old internet protocols like Archie and Gopher, you'll realize that everything was different than just the web running on the internet. And as we realize that there's more to the internet than just the World Wide Web, when there's more to data transmissions than just a web browser, when there are more places that are receiving and sending data that aren't just the Amazon Web Services data centers, you'll realize that while we do appreciate that companies are trying to optimize TCP to solve their particular challenges, we're never really going to get rid of it. So while TCP might be dead, it's still got a lot of life left in it. I want to thank everybody for joining me for this episode of Tomversations. We're getting down into the dirty parts of the protocols, and the show notes that I'm going to link are going to have a lot of great discussions about a lot of things, such as QUIC and SRD and UDP. And there's a lot of great ways that you can kind of understand how these protocols work, whether you're starting out in your networking career or it's been so long that since you've had to deal with them that you've kind of forgotten. We'll be back with another great episode in about a month or so. Until then, I recommend that you check out our other great content at gestaltit.com. We have a lot of things for you to consume, whether it's our on-premise IT podcast, our checksum web series, or other great articles that you can read. Until then, thank you very much for tuning in and listening to this great conversation. I hope to see you soon.